on the West County class site. So do it 2 weeks from now, and it has to be done. Everything is done in groups of 3. Who does not have a group yet of 3? Oh, that's not bad. Really? Wait, who has a group of 3? Wow, okay, that's actually cool. For those of you who don't have a group, no worries. We'll hash it out today. We'll just have everybody leave the room, and then we'll just kind of stay here and then figure it all out. The people go out groups and leave the room, and we'll figure out in a few minutes. And then, so it's due in 3 weeks from now, and in 3 weeks from now, you'll basically hand in about a 2-page report saying what you've done. And so, yeah, I mean, that's that. Okay. So now, the slides are up. All the slides for the next few weeks are actually, I put them up, and when I get once I'm done with the section of the class, and I have all the scribbled up notes, then we can actually, I'll post a new version of things with the scribbled up notes, like my writing on it. But let me just show you something that you should be very well aware of, is that, well, hold on, let me connect this thing. How do I turn these lights off? That's a very important question. You know, there should be a little button where you can say, okay, how do I do this? I can't see the thing, it's really annoying, you know? Wait, what? So, as you can see, this is, you know what this is? This is the clean version. You know what the clean version is? The clean version is the one that I wrote ahead of time. So I know what we're going to talk about, and that's kind of the clean version of the slide. And then there's the one that we... Whoa. That's a clean version. It doesn't look, maybe it doesn't look too clean to you guys, but it's relatively clean. Compared to the version that we do in class, that's the version we did in class. So, okay, that one's pretty lame. But you can see that, for example, this is the one we did in class. So basically, every slide will have the one we did in class and then the one that's the clean version, which is, and so my point is, what I'm trying to say is, the stuff that we do in class, we're going to write on the slide. It's not like you will die if you don't see the version that I wrote, that I scribbled up. I will post those eventually once we're done with each section of the class, but the ones that are the clean version are already online, so they have all the answers. Speaking of answers, the reason why I post them up like that is because some people really like to see the slides ahead of time, but they also have all the answers to all the nifty educational questions that I ask. You know, I ask questions with pedagogical, you know, kind of, so it's like I ask you to figure something out in class, and if you look at the answers, it's no fair, it's cheating. Well, I mean, you know, it's not cheating, but okay. So, last thing we did was this one, which was loop invariant. Whoa, check it out. See, this is a great example. This is what we did in class. This is what we wrote with some scribbles and all this stuff. And this is the clean version that kind of I had written ahead of time. So, loop invariant code motion, what it means is that we're taking some code and we're moving it outside of the loop, because that code, every time you run you run in a loop, it evaluates to the same value. So there's no point in repeating every time. You can move it up there. There's one last thing I want to talk about, which is this example. So what do we do here?
Inline?
Inlining. So inlining, okay, hold on. What is inlining? Inlining is you take a function, and you take the function call, and you take the body, and you just copy it in instead of the function. And we'll see later on why you want to do this. I mean, there's many reasons you want to do this. One is that you get rid of the overhead of the call. That's one thing. But there's actually another reason, which we'll see right this very second. So what happens now? Oh no. Uh-oh. Oh no. Oh. So now, what is this going to be?
H times W.
What?
H times W.
So H times W, right? So actually, what I'm doing here is I'm cheating. I'm totally cheating because usually the names are not the same. Usually this is going to be named differently. So actually, what you usually get is actually copies. So what happens is this is like H1 and W1, and this is H1 times W1. And so what you actually get is you plug in this thing, and it becomes H1 times W1. And then you insert copies here saying, well, H1, this is your, is equal to H, and then W1 is equal to W. Right? Yeah.
How difficult is it for the compiler to use optimizations to determine that H and W, say, aren't modified in the function and it doesn't need to bother copying them?
Well, I mean, the copy here is really the only thing so the copy is not to preserve the values. The copy is just to pass in the values into the parameters, right? So your parameters here may be called, maybe this is, let me make it just even clearer, so let's call this X and Y. And it returns X times Y, right? So basically here you just have to set X to H. Or you have to do some renaming. I mean, that's the other thing. Right? So either you have to rename these things with H and W, or you can do it this way, and then if you do it this way, you know what happens? What happens? Well, actually, the one you could do here, so you can do constant propagation, but you can also do copy propagation. What is copy propagation going to do? It's going to put this H here, right? And it's going to basically put this W here, which gives the same effect as renaming. But so now, if you do that, you get what we originally had, which is H times W. And now what happens? Constant propagation. So this becomes 4, and then what happens? So one thing to keep in mind here is that, notice how a lot of these optimizations by themselves, may seem like they're not that useful or important, but actually they're very useful as post-passes to clean things up, especially after, for example, things like inlining. When you do inlining, a lot of these optimizations are for cleaning up all the mess that happens after that and kind of tidying everything up. Okay. So basically, there's a whole bunch of optimization themes. I mean, it's not rocket science, but this is kind of in terms of traditional optimization that you find in compilers. This is the kind of oh no, what happened? Oh, I know what happened. Just going to back. So, if you have assignments that are not used, basically just don't remove them, obviously. Try to compute things at compile time, right? So, constant folding is a version where you take, 5 plus 3 and compute it at compile time instead of at runtime. Inlining is the same thing. It's almost like you're doing a function call, and the passing of the parameters, you're doing all that thing at compile time instead of at runtime. There's this thing where you have, sometimes when you run a program, there's redundancies. There's some expressions and values or computations that are computed multiple times, and so you want to basically compute those as kind of the fewest times as possible. And that's where things like common sum expression elimination, we saw partial redundancy elimination. There's actually various kinds of, so loop invariant code motion was also a version of that. There's also something called partial redundant code elimination, which you haven't seen, but this actually loop invariant code motion also is the thing. You're running over and over the same computation you pull out of the loop. If you are going to compute it, then basically you want to compute it using the cheapest possible operator. So that's where you take some operators and find simpler operators that do the same thing, or simpler sequences of operators that would compute the same thing. Whenever you have optimizations, one of the purposes is actually to enable other optimizations. So when you do constant propagation, copy propagation, a lot of times it's to basically enable other things. For example, when we did this, notice how here we didn't see this shift by 2 until we got this 4 here. And the reason why we got this 4 here is we were able to propagate it from there. So once you start doing certain optimizations, they actually enable other ones. And you know, the other thing is, and pointer analysis, also we saw pointer analysis, that's actually a big enabler that actually enables you to reason better about your programs and do better optimizations. And then the other thing is compute, you know, if you don't need the code, just don't put it in there. So a reachable code elimination is an example of that. And this is actually, you know, in general, it could be a big deal, right? If there's libraries that you don't need, don't put them in your executables. If there's pieces of things that are not useful, just don't put them in your binary. Okay, any points on this? So part of the goal of this section was to give you a feel for some optimizations for some names that we can actually kind of, you know, we can use them as examples when we're going to see things in the next kind of few weeks. Does that make sense? Any questions?
I have a question.
Yes.
What about if we have, you know, something like one of those emerging objects, like something parallel or something like academia? We just like modify these accordingly, or do we consider it like a subset?
So there's different kinds of things there. So one is you can have architectures where you actually can issue multiple instructions at the same time. So there's I mean, this has been actually out for a really long time for like things like MMX on Intel, or they're calling it SSE now, things where you have the same instruction, multiple data, right? Like SIMD kind of thing. And those are the whole bunch of research. People have kind of figured out ways of taking loops and kernels of loops and kind of making them so that you can basically dispatch multiple things at once. A lot of it ends up being something called, I mean, you basically look at the dependencies and you kind of figure out which things can run in parallel, which things don't depend on each other, right? So if there's, once you put the dependencies in your instructions, if two things don't depend on each other, then they can run in parallel. Then there's more coarse-grained stuff, like when you actually have multiple processors, right, that you can actually use, or multiple threads, and that gets a lot more complicated and a lot harder. And a lot of times, actually, that's really, really hard to do automatically. Right? A lot of times you have the programmer kind of give you hints, or the programmer gets involved in actively telling you where the parallels are. I mean, so MapReduce is a great example of that. Right? In MapReduce, the programmer kind of writes their application in a way that actually gives you some flavor of where the concurrency is. But I mean, there's a lot of things you can do, and those are more advanced things.
Where do we draw the line? In our examples, we talk about, oh, there could be another thread doing something. That implies that we have like full strength.
Right. So a lot of what happens when you optimize one particular piece of code is you have to identify pieces of the data structures that are shared amongst multiple threads. And things that are shared amongst multiple threads, some things are not shared. Some things are actually just thread local, and you can do analysis that figure out that this part is only part of this current thread. And those you can kind of just optimize away. For example, a local stack variable, right? I can do constant propagation on the local stack variable, and I know that unless I do something really stupid, like take the address of that local variable and send it out to another thread, which is really stupid, well, not stupid. I said, you can do that, but in Java you can't. Actually, then I can know and I can reason about my local variables, even though there's other threads doing all this other stuff. But when you talk about the heap and field and objects, reasoning about those is a very, very much more complicated thing. Then you have to think about synchronization, about locks. And in fact, we will actually talk about how we can actually infer. So there's this thing called lock set analysis, which we'll talk about, where you actually figure out using analysis where the locks are being held and where they're not, and what variables are being protected by what locks, which actually then gives you a sense of what concurrency is going on and how to reason about your program in the face of multiple threads and lock articulation. But those are all we'll cover some of those things later on, but that's kind of gives you a summary of high-level summary. Okay, so let's talk a little bit let's talk a lot about data flow analysis. Not a little bit, we're going to talk a lot about data flow analysis. We're going to talk about data flow analysis for the next probably like 3 or 4 weeks. And I know that this seems like, oh my gosh, that's crazy. How can you talk for so much about data flow analysis? This is because it's such a cool, amazing topic. It's been around for like 30, 40 years. It's really it's a core foundation of kind of analyzing programs. So, okay. So what is data flow analysis? So what it is just a common framework for expressing algorithms that compute information about a program. So, there's a whole bunch of, we talked about all these different, optimization, and each one kind of needs a particular kind of information about a program. Data flow analysis is one of the frameworks. There's a handful of others. It's not the only one. There's maybe 2 or 3 others. But this is one of the main ways of expressing algorithms that compute information about a program. So why is such a framework useful? Well, there's many reasons why it's useful. So it provides, and so they all stem from the fact that it provides a common language for us to talk about these algorithms. And that in turn makes it easier to basically communicate your analysis to others when you come up with the coolest, best, and most amazing analysis in the world and you want to write it up in a paper. This allows you, data flow analysis allows you to kind of present it in a way that people will understand and expect to see. It also allows you to compare analyses, right? So you can have 2 analyses and say, how are they different? Well, here's how this one does this, here's how this one does that. I mean, kind of compare them because we actually have them expressed in a similar kind of framework. We can also better understand when we read a paper how those techniques in that paper will actually impact our analysis because they're expressed in a similar way. And one thing which you will learn in this class very hands-on is that it actually allows you for reuse of implementation. In particular, once you have a framework for doing this kind of stuff, you can actually build an engine that does your data flow analysis for you. And that's what you're going to do in the second part of the project, not the first part. The second part, which will start, in the second half of the quarter, you're going to build a data flow analysis engine, and then once that's built, you don't touch it anymore. You basically, when you want to compute some information about a program, you just give it some parameters and some things, and the thing will just compute the information for you. Okay. Is everybody sold? Not yet. Maybe. This will be really cool. So, one of the first things you got to do when you do analyze a program is you got to represent the program. You don't want to do it as a string. It sucks. Strings are horrible. So you want to represent it in a better way than just kind of raw string. So there's many ways to represent programs, and later in the quarter, in the kind of second half of the quarter, we'll talk about really interesting cool ways of representing programs. But for now, just to get us started so we can do data flow analysis, we will assume that we have a very, very common representation which is called a control flow graph. Have you heard here what a control flow graph is? Can someone tell me what a control flow graph is? Oh man. Maybe that was too easy. Let me tell you. It's written on the slide. It's written on the slide. So control flow graph is a graph where every statement, well actually there's many different versions of the control flow graph, but the simplest version is every statement in your program becomes a node, and edges between nodes represent control flow, which means that, what are the possible next instructions? So let's see a really simple example. Here is a piece of code, and there is a control flow graph for that code. So every node is what? Is a statement, and we have edges that represent where the next statements are, and this is a conditional. Conditional has 2 branches, a true side and a false side. Okay? So, does this make sense? Okay, so there are twists. There are bells and whistles on control flow graphs. One of the bells and whistles, which is actually important for you guys to know about, is we'll not use it much in the class, but it's actually important to know about. It's called basic blocks. Do you know what basic blocks are? What's a basic block? Yes.
piece of code with a symbol from an entry and a symbol from an exit, like that.
Yeah, so it's usually, basically, it's a piece of code with a single point of entry and one, or sometimes there are actually variations that can actually allow you multiple points of exit. The reason why we talk about these basic blocks is because actually when you think about this thing here, like this and this and this, really what you could do is instead of having these three nodes, you can actually basically cover them together in what's called a basic block. And then you say, this is one big node that has three instructions all at once. Because the control flow in a basic block is just straight line. That's really the most important thing. Inside the control flow block, once you enter, you go all the way to the end. That's kind of the vanilla version. And so here, we can have one basic block, one basic block, one basic block, and you can actually even have that a basic block with two outgoing edges, and that makes the control flow graph a little bit simpler. But for us, I would like us to keep it in this way where every node is a statement in the graph. Whoa, questions? Yes. Yes, so what, wait, you mean these nodes?
No, it's control flow block.
Oh, you mean the basic blocks?
Yeah.
No. No, they're just a convenience for representing the program. In general, they don't. You can build your representation in such a way that your basic blocks actually kind of are made, run atomically, but there's no, in general, that's not the case.
I just thought it might simplify data analysis, because then you don't have to care about interrupts or anything like that.
Sure. You mean yeah. So it would in terms of concurrency and things like that, it would, yes. For all of these things, we will always kind of for the class, in class, we will always assume that every node is a statement. There's no basic blocks. It'll make it easier for us to express our data flow analysis. And furthermore, every statement executes atomically. Every statement executes atomically. Yes. Well, two questions.
What about exceptions?
Oh my gosh, you guys are like, I'm trying to get to data flow analysis, and you guys are, great question. So there's many ways to represent exceptions. They create a lot of problems. One way to do it is that you just add extra edges that basically tell you where exceptions can happen and what the flow of, what the control flow would be because of the exceptions, right? So for example, let's say this can throw. Let's say this is some kind of field actor that could cause an exception. Now that is a null pointer exception, so you would have to kind of, draw an edge from here to the end of the procedure, saying that this could possibly exit the whole thing with a null pointer exception. Yeah, absolutely. So that's how you can actually accurately model exceptions in this kind of model. Yes.
Ja, bei Statement, wenn die Model the exception in the point method, it doesn't have to be executed automatically because it could be really large thing.
So actually, no. In this case, we will basically statement will mean statement in our intermediate representation. Okay, which will mean it'll be a statement that will be a very simplified form, and it'll become very clear why it's important for us to do it in our intermediate representation as opposed to a source language. It'll become very clear. And actually, by the way, I lied. I didn't mean that it's atomic. It's only atomic for atomic statements. For statements like this, but for function calls, obviously it's not atomic. I mean, it can go and do that like that. Yeah.
How do we represent jumps that are kind of in runtime that are resolved at runtime?
How do you represent jumps?
If the target is resolved at runtime.
Right. So what would be an example of that?
It could be that some sort of function which could be calling either the parent or the child.
So you can have function pointers, you can have method calls, you can have various kinds of, so basically the way you would do it is you basically, or you can even have indirect, you can have bizarre things with case statements that kind of do weird branches. So in all of these things, what you have to do is you have to build what's called a conservative approximation of the control flow that could happen. Okay? So what do I mean by conservative approximation? This will be something that we'll be using many times. It has nothing to do with political affiliation. Okay? What it means is that we want to have a control flow graph so that it over-approximates the set of possible transitions that can happen at runtime. Okay? So in particular, if it's possible that some kind of this can happen, we want to analyze the program and put an edge there. And so actually, this is a great example. You know, here, it may be the case that this is always evaluates the truth. And so it turns out, maybe the program always goes this way, but we still have this edge here, right? Because we kind of think it's possible, but it may turn out that it never goes down that way. It always goes down this way. And so our control flow graph and our edges represent an over-approximation of what is there, what happens in reality when you run the program. But it would be really bad to miss edges, right? So if it's possible for something to jump somewhere, you don't want to miss that. You want to basically make sure you have that there. Yes?
How do we represent flow that's represented by something dynamic,
Like what?
like say, you jump X lines of code ahead, but X lines at runtime.
Right, so that's the same question here. I mean, basically, you would have to compute some kind of approximation. You would have to basically figure out all the possible targets and figure out all the possible places that it could go to. Right? I mean, you have to, otherwise, I mean, there's no way, right? I mean, same thing as exception. When you have an exception, you have to figure out. Okay, but hold on. One more question, and then we got to move on because we're getting sidetracked. We can talk about these things. This is so much fun, but we got to get to the different ones. Otherwise, we're not gonna be able to. Yeah.
Too hard to start.
Oh my God! No.
Intermediate representation.
Wait, what?
There's supposed to be an intermediate representation.
Yes.
So that's supposed to be pre-optimized or everything is what you're saying.
Wait, what?
Pre-optimizations and everything. That's how we're keeping it.
Yes. This is basically, you can think of it as you take the program and you just bring so actually the first thing you do is you parse, usually the first thing you do is actually you take your program and you parse it. I know I said I'm not going to talk about parsing, but you parse it into an AST. An AST is an abstract syntax tree, which just gives you the syntax. And then from there, you can relatively easily build a control flow graph by just looking at the jumps of labels and stuff like that, and the while, and then the while nodes and all that stuff, and you can just build these control flow graphs here. So what's the second part? Wait, you said there were two parts.
The second was that this could then be an input to the optimization. That's why we want to be conservative.
Absolutely, exactly. That's why we want to account for all possible. If it's possible at runtime for some control flow to happen, we want to have it represented in our control flow graph. Woo! Okay, that's it. No more questions. I'm going to quickly. Oh my gosh. Woo! Okay. Wait, what happened there, guys? That was so quick, I don't even know where we're at. Oh, so we will do an example. So we will do this through an example. The first thing we'll do is we'll build all of this data flow analysis stuff through an example first. So the example I want to do is something called reaching definitions. So the idea here is I have a variable, and that's being used at a particular statement. So I have a statement, and it uses a variable. Call it X. I want to know all the possible assignments to X in the program that could have created the value that I'm reading off here. Does that make sense? I have a variable, I read X, I want to know where could this fantastic value of X have come from. Now there's many reasons why you could want to do this. One possibility is that you can actually use this information to do constant and copy propagation. So here's how you would do that. Now this is not the best way to do constant and copy propagation. Constant and copy propagation, but it is one way that's valid to do if you want to. So let's say I have an X, and I look at my program and I do this reaching definitions analysis. And this reaching definitions analysis, so this is the use of X. This is what this means. This means that you're reading X. And so my reaching definitions analysis will tell me that when I do my analysis, it'll tell me that there are 3 possible assignments to X in the program whose values I could be reading here. And if I go and I look at all those assignments, and all those assignments are 5, right, then I can replace this X with 5. Right? Does that make sense? So I'm looking and I see, oh, these are all the places where this X is being assigned. It could possibly come to that value there. I can basically use, I can just propagate this and say, well, you know what, this is 5. You can basically do these things called def use change, which is basically, we'll see actually a little bit later, which is basically connect a variable. So for example, let's say your IDE, right? And you have a variable X. and it's null. And you're like, oh man, null pointer exception, this totally sucks. And then you're like, where could this X have come from? Or you want to kind of track it back, see where it came from. So you can actually follow these things called def use chains, and you can actually present that to the programmer. You can also build other representations using this thing. You can actually build what are called data flow graphs, which we'll talk about later when we talk about representations. So let's try this out. Now, this is our example. I'm going to write this in the following way. Now, I really don't want you to think of this as a basic block for now. I really want you to think of this as this visual trigger, which means that underneath the hood, there really are 3 different statements here, 3 different nodes with edges between them, okay? So that's, I mean, nothing changed here. I just changed the visual way in which this program looks. And so that's our program. And I've labeled the different things. So now what? What happens now? Well, now, let's take a look at what the reaching definitions would be for this program. So here, for example, what are the reaching definitions for this X? What are the possible assignments to X?
Whatever's on line 1.
What? Okay, that was pretty easy. What about this one? Okay. How about this one?
3.
2 and 3? I heard 2 and 3.
Wouldn't it be 3?
Oh, how can it be 2? Right, so the value will never come from 2, right? So we can basically say that it just comes from 3. What about this? I know that it looks weird because it's on the left-hand side of an assignment, but that P is actually a read, right? We're reading P there. So that's a read of P, because it's a variable. Okay, so where does P come from? Well, that comes from 4, right? Okay, what about this X? So that could
5
come
or
from
6.
5 and from 6. Awesome. What about this Y?
5 or 3. Oh, no, not 5.
Wait, so it comes from 3?
Mm-hmm.
This could come from 7 too?
Even X, yeah, but X
Uh-oh.
will come from 7.
You think this should be 7 too? Aha! So this value of X could come from 7. Okay, this is very important. Huh? Why is it very important? So let's suppose we had a reaching definition analysis which didn't say 7 here. And let's say my program was like this. I had a 5 here, and I had a 5 here, and I had 6 here. Oh, why do I use the same number? Let me put 10 here. So I see that, oh, X could come from 5 or from 6, and both those values are 10. This is amazing, this is awesome. I'm going to replace this X with 10, right? Sure. But then, this P may actually point to X, because we don't know anything about P. I mean, there's nothing that tells you what this P is. This could be P equal address of X, in which case this actually sets X to 20, and then my optimization is wrong. Okay? So in this case, it's actually important not to forget things that are actually possible assignments, possible reaching definitions. Does everybody see that? That it's important not to miss that stuff. Yeah. Yeah, it doesn't matter actually. The point is you're doing star P. The star P can actually assign X.
Yeah, but we don't actually find what people.
Yeah, but this could call a function. This could basically do address of X. or I could call a function foo, where you send it the address of x and the address of y, and it has a whole bunch of other things, and it somehow computes something for p, which could possibly be the address of x, or the address of y.
We know what P is a folder and the address was the same in your output program.
Yeah, but that's not the point, right? I mean, the point is that the point is, this statement can modify x. So we better include it in our reaching definition. When we say, where does x come from? If I ask you, where could x come from? This value that I read here, where could it have come from? It could have come from this assignment, right? In fact, this program could actually have x be 20 here, because p could point to x, right? So, okay. So, what's next? So this is all fine and dandy, but this is not the way we want to do it, right? Because this is like us looking at the program and being like, yeah, well, this, I mean, yeah. You don't want to, no, not the way to do it. We want an automated way of doing this, okay? So this is where, okay, that's the answer. Oh, wait, hold on. Oh, man, actually, we talked about this already. When is the computer information safe? When is the computer information correct? Right? So, as we saw, you're not allowed to forget 7. If I forgot 7 there, that would be a bug in my compiler. That would be a bug in my implementation. Right? Someone could file a bug and say your compiler is doing weird stuff there. But actually, let me go back and say, what is here? Actually, what is here? Actually, where did we do it? Wait, hold on. Here. So I wrote this down, and then you guys were like, no, how dare you can't put 2 there. It should be only 3. Okay? Let's suppose that I actually say, no, you know what? I'm sorry. I don't want to change. I really want to return. I really want to say 2, 3 here. I want to do what I want. Is this a bug?
No.
It's not. It's overly, what happens is, again, it's overly conservative. It approximates, it just says that it's possible the value could come from 2. But in fact, it never does. Now, what that means is this additional 2 here will not cause you to create incorrect optimizations, but what it will do is it could possibly cause you to not perform certain optimizations that you could have otherwise performed. So here's the example for that. Suppose that, for example, this is 10, and this is 20. And here you don't know anything about these, I'll remove them. So, if I put 2, 3 here, right, I'm going to say, oh, this value could come from 2, so it could be 10. Oh, it could come from 3, so it could be 20. And then you're going to conclude, you know what, I can't do anything with this y. But in fact, you can. If you have the more precise information, if you have a better, so sometimes this answer is better. It's a better answer. It allows me to do more optimizations. Now I can actually say, oh, this y is only 20, I can transform it to 20. So we saw that basically what happens is, you can actually, it's always safe to add more. You can always just add more things in there, and it won't cause any problems. But it's actually, what the problem is that when you're not allowed to forget things that could really happen. Okay, so for example, actually, if I can even say 7 here. Somehow, like, I got confused, I didn't know the control, I was like, okay, 7. This, somehow, but of course, there's no way this will happen. But that's not a bug. It's just it's what's called an imprecision. It's not going to lead to correct this problem. Okay. Does that make sense? So what does that mean? So we can always have more bindings than the true answer. We can always have more things, but we can't miss any. Okay? Does that make sense? Does everybody, any questions on this? Okay, so now we did one example where we actually just came up with the answer we really wanted. Now the reality is, data flow analysis frameworks are geared towards a stylized form of information that they compute. there's different versions of this, but the one we're going to see here is that we're going to have a data flow analysis framework that will compute at each program point some piece of information. A program point in a control flow graph is just an edge in the control flow graph. Okay, so an edge in a control flow graph is basically a point between two states. So our data flow analysis framework will compute for every edge in the control flow graph some piece of information about the program. That's how our framework will be set up. Okay? So, what we have to do is we have to generalize our problem to this setting. And so what we'll do is, for each program point in the control flow graph, in other words, for each edge in the control flow graph, we'll compute a set of definitions that may reach that point. Okay? And the notion of safety remains the same. So let me give you, let's just actually work through it. Actually, hold on. I'll just skip this. Let's just work through the example first, and then we'll see what this means. So really what it means is you start off here, and this is a point, this is the entry point, this will be the empty set. Right after this statement, we'll basically compute the information that the variable x comes from statement 1. So this basically tells us that x comes from statement 1. Then we go here, this will tell us that x still comes from statement 1, right? If you want to look up x here, it comes from statement 1. And then where does y come from? It comes from statement 2. What about here? x1, y3. So basically, at every point what we're doing is that we're computing for every variable which statement it could have come from. Okay? Okay, wait, what are we doing here? Okay, this is not the, what about here? X goes to 6, y goes to 3. What happens after this thing here? Whoa, 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 whoa. What happened? Whoa, hold on, hold on. Hold on. P. Where did P go? Hold on, hold on. Well, we're doing this too fast. We're doing this too fast. We're making mistakes here. Hold on. So this is the x is 1, y is 3, and we forgot our P. So P goes to 4, right? So here we're going to have a P goes to 4. And what about here? Oh boy, I'm scared. Can we not do this one? No, hold on.
It's okay.
You want to do it? You really want to do this one right now?
Yeah.
Oh, okay. I want to do the other branch because the other branch was easier. Okay, fine, let's do this. Okay, wait, so what happens? So, x goes to what?
6, 7.
So we'll just represent that as two different volumes like this. So x goes to 6 and x goes to 7. We could also represent the way you said, which x goes to a set, but I'll just represent it this way for now. What? Okay, now what?
Y 3, 7.
Hey, y3, y goes to 7? Okay.
And P4, P7.
Whoa.
That'd be a weird program.
P4. What does that mean? That's why I was really scared of this thing. So, hold on a second. So first of all, let's just look at, okay, we all agree on this one, x6, x7, right? So 6, now x could either come from 7 or from 6. Y could come from 7 or from 3. P could definitely come from 4, but you're saying P could possibly come from 7. So that would basically be, that would be a situation where basically UP is equal to the address of P. Right?
Sure.
Right? Is that what it is? I mean, P, wait.
Could happen, I suppose.
That could happen. What's the problem with this? Oh, in C, you could definitely have it.
Yeah.
So star Q would just be an assignment to P. There's nothing weird about this.
It's a lot weird about it.
What?
It's a lot weird about it.
There's a lot weird about it. No, you're absolutely right. So in a language, in some languages like Java, or in languages that have a really strong type system, I mean, you wouldn't even be, you have to use some kind of weird typecasting to get this to work, because the type of this P is a very bizarre type. But in C you can definitely do this. And the point is, you know, as we said, so okay. So we now have to decide, are we going to put this or not? Yes.
I don't think it should go there because we're assigning the star P, e.g. the value that P points to, but not the actual value inside of P
Yes.
itself.
No. Well, wait. No. This is the problem. This is why P mucks with your brain a little bit. Because the problem is P can point to P.
Oh.
Right. If I write this program here.
But if P can point to P, then, and P the pointer, then it means the first P is double.
Right. That's why the typing. That's why the typing is really weird. But in C, you can definitely do this. I mean, in C, you can definitely do this. You just need to use some weird typecasting. I mean, you can. I'm pretty. I mean, what?
You can definitely do that.
You can definitely do that in C. Now, here's the thing.
You may not want to.
If it's doable, okay, there's another thing. Another axiom of C is that if it's doable, someone has done it. In some piece of code that actually works, right? So, but here's the thing. So there is a possibility. So if it's C, and you can't trust the type system, actually you can write code like this. And so in some sense, you really do need to put this PR7. P could be redefined here. Now, you know, if we're debating whether or not to put this, right? We're having a debate, we're not sure. What's the safe thing to do?
Put it
Just
in.
put it. So let me just instill this kind of philosophy in you that sometimes, you know, if you're on the fence, you're not sure, putting something in there will actually make you more conservative, which basically means you will at least not create buggy or incorrect optimizations. Now, this may prevent you from doing some fancy optimization later on, but, you know, for this kind of corner case, it's unlikely, so you just might as well put it in. Okay, what about here?
So,
Oh, wait, we didn't do the other side. Yeah.
so basically, whenever we have a pointer assignment, we just go ahead and assign every variable we have actually pointing
Yeah.
doesn't sound too foolish.
Zero.
I could be wrong.
Absolutely, it's horrible. It's horrible, but hold on. So really, what you're doing is this assignment could possibly assign any local variable, and so it could be x, y, or p. Okay. Now there's ways of you're absolutely right, but the way you can do this, you can actually have a pointer analysis. So if you don't even have p, yes, you have to be conservative. This is why pointers really kill you, because this is a problem, right? The problem is when you're building this, you have to be conservative. You have to basically assume that you can't, if you miss one of these, and it turns out that P really pointed to Y, and you miss this one, then you can actually get incorrect results when you do your analysis, when you do your optimization. So it's actually important to account for all these things. Now we can have some additional information, a point analysis, that tells us, for example, if this, for example, says X, then we can learn that P definitely points to X, and then we can basically use things from there. Right? But in the absence of that, which right now I'm going to say we don't have that information, then you have to be conservative.
But, in a language like C, isn't there a possibility that, let's say, the pointer could point to anything even outside of local scope, as long as it's in the addressing space?
That's absolutely right, but I don't care. Right now, all I'm doing is I'm computing the reaching definitions for my variables that I care about in this program, in this particular procedure. So, I mean, yeah, I could point to variables in other places on the stack, but right now, I just care about these particular X, Y, and P variables, right? So, yeah.
This is too far ahead to ignore it, but if we're doing optimizations, we'd be updating this as well.
Updating what?
The control flow graph, or the data.
Yeah, so there are ways of actually, so there are ways that when you do certain analyses that will give you better information for doing stuff. Sure. Sure. Right, because basically you notice how if you have a bigger set, then the bigger the set is, in some sense, the worse the results are. So if you make the set smaller, you can actually perform more optimizations, but the problem is if you get it too small, and you forget some things that are real, then you can get to basically incorrect optimization. Okay, so let me write this down. So what happens here, you have x goes to 5, y goes to 3, and p goes to 4, right?
Mm-hmm.
And what happens here, what do I do here? Combine, I think the union of these two things. I'm not going to do it right now. I mean, it's just going to, basically going to give you the union. And so this takes literally the union of these two things. Okay? Okay, does this make sense? So now if I go back to my original, so this is not the original question I had. The original question I had was, I have this x right here, where did it come from? And so, but now you can use the information you just computed because you have this whole information about all the variables, and now I can say, oh, x is, I can look at the incoming information right before this statement, and I can say, oh, I can read off, where does x come from? It comes from just 1. I can, if I want to know where does, let's say, this x come from, I read whatever information I have here, and I see that x will come from where? 5, and 6, and 7. Right? So this gives me a way of reading the information that I wanted originally. So notice the trend. I started with a particular problem I wanted, which is for every variable I want to know where it came from. I generalized it, so I set it up so that at every program point, every edge in this control flow graph, we compute some piece of information, and then I use this information that I computed by my data flow analysis engine to then extract the thing that I really wanted originally. Yeah?
I think there's something we do not represent here. So x can come from 6 or 7, but if it can, I mean, it's, never mind. Okay.
Right, so I mean, if P doesn't assign X, then X comes from 6. That's what's happening. So, okay. Woo. Okay. This is not the way we want to do it, because we're actually still doing it by hand. So what we want to do is we want to have a systematic, algorithmic way of computing this information. So, the way we're going to actually do this, okay, those are the answers. Look at how much neater this is. It's a little bit neater. Not totally neat, but just a little bit neater. So, so here's one of the key ideas of a data flow analysis engine, and this holds across all data flow analysis engines, is that the idea is that you want to, we're going to model this data flow analysis as solving some constraints. And each node in the control flow graph will impose constraints. So basically every node has one edge coming in and one edge coming out. Well, that's not true. Some nodes have 2 edges coming out, some nodes have 2 edges coming in, but more or less they have some edges coming in and some edges coming out. And each one of those edges in the control flow graph has some information, right? So there's some edges coming in, some edges going out, and each one of these edges has some information on it. And we're going to write constraints that will relate the information, for every kind of statement, that will relate the information on the incoming edges with the information on the outgoing edges. And that will tell us how the information should basically, how each statement will affect the information that we are actually computing. Okay? So let's take a look at how, and then once we have all these constraints, we're going to basically solve these constraints, and the solution to these constraints will be the results of our data flow analysis. So let's take a look at what this looks like, the constraints for reaching definitions. So let's say we have a simple assignment, okay? And a simple assignment will have one incoming edge and one outgoing edge. And I'm going to have some incoming information. This incoming information will be a binding of the kind we had before, where it'll tell us that maybe, A comes from statement 5, B comes from statement 10, B can also come from statement 11, etc., etc. So it'll be a set of these things. That's what in will be. And here, we're going to basically constrain out to be a function of in. Okay? So the way we're going to build things is in the 4 directions. So we're going to write the out in terms as a function of the in. Okay? So what is the out going to be as a function of the in? So we're gonna take in and we're gonna do some operations on it, and that will produce out. Yes?
Should be in minus whatever x we have in there, plus this factor.
Absolutely. So let me rephrase that. It's in minus whatever we have for x, because this will cover all previous things. And then we need to remember that after the statement, x will come from f. Okay? So the way we can write that down is like this. So this is a set, so we can do x minus, so in minus, I'm going to just do x arrow star, x arrow f. So this is basically the set of all x arrows, so any binding. And so by subtracting the set, I'm guaranteeing that I'm removing all the x's. This is kind of a math notation. And then I'm unioning in the element that x goes to x. Okay? Does that make sense? Are we all on the same page? So we remove all the x's we had from before, and then we add that x goes to x. And now we have out as a function of in. Okay? So given in, we can compute out. So in some sense, the constraints here are in the forward direction. We get out from in. So that's how the constraints are set up for this problem. Okay, what about this? What about the star p?
We don't have
Oh,
to
boy.
subtract.
You don't have to subtract?
Yeah, you just, it's in plus,
Wait, hold on. Okay, so you don't want to remove anything, but then what do I want to do? Wait.
you want to add to all of them.
So, any variable, so let me write this like this. So V is a set of bars. So basically I'm going to add, for any variable V, I'm going to add the V arrow S, right? So for any variable V, I'm adding the V arrow S. Okay. Now, if we had information about P, so notice how we're not removing anything, right? Now, but it's very, so if we had information about P, what could we do better? Could we do something better? So we can limit things. So how do we do that? So let's say that I give you a make point to analysis, which given P, well, so make point to P will tell you all the things that P may point to. What's that?
Yeah.
Oh yeah, so that's one way. So instead of having VB all the bars, we just have VB. V is, we could just basically say V is in the set of make points. So basically, for everything that is in the make point to of P, right? Anything that P may point to, this could possibly be an assignment to that thing, and therefore we have to track it as that variable may come from S now. Yeah?
But it says that contains pointers and stuff, how does make point to that?
No, it's the make point to only, it's not transitive, it just gives you the immediate thing, and that's what we care about here. We just care about the immediate, so think about this. Make for now, because we're going to have a whole section on pointer also later on, but think about it for now, that make point to returns, for now we're going to do two variables. So we're not going to have dynamic allocated memory. It returns you a set of variables that P may point to. And that's set to be all the variables if somehow the analysis gives up and may give you everything, but maybe it's going to be more precise than that and it only gives you a subset of those things. Yes? Right, so, okay, so So here, what we've done is we have added things. But what about deleting? We have not removed anything. There's no way to remove anything. The only situation, and this is actually kind of a subtle issue here, which is really interesting, the only way we can remove information here is if we know exactly what variable is being assigned, right? If we don't know that it's one variable being assigned, then it's all bets are off, and we don't know for sure. So, but we could, if we, for example, so this gets into a little bit of a complicated situation, but you're right. So one way we can look at it is that if we are only doing, we're not doing there's no nulls, there's no weird kind of things like that, it's only variables, then well, it's confusing actually. So okay. What you're saying is, if main point to contains only one thing, then that means that P definitely points to that thing, and therefore we could just delete it. And the way that I'm going to think about that is that I'd like to kind of have a separate analysis called a must pointer analysis, which returns to me a single variable if you know that it points to that thing, or just the empty set if you don't know anything about it. The reason I'd rather do it that way for now is because there are subtle issues. For example, let's say that this may point to actually includes also null, right? Because actually, even in the setting where you only point to variables, something can still have a value null. So then what if may point to contains null, and that's only one element, then what do you do? Well, then I don't know. Then it gets a little bit confusing, because then it gets back to, now this is going to throw an exception. Does that mean that do we not care about those things? It's kind of it gets a little bit confusing. So that's why I want to avoid the nullness issue, because then you get into the semantics of what does it mean to have a null pointer exception. Do you have to preserve the behavior of those null pointer exceptions or not? We talked about how it gets into a lot of mess when you do that. So the way that I'd like to write it out is like this, which is that basically, if X is in a must point to set, and must point to computes a set, and that set is a singleton set if you have the information that it points to a single variable, and it's just an empty set if you don't have that information. So it's really the same idea that you said. The intuition is the same, which is that if X points to only one variable, then you can remove that binding. And you can remove it for any statements, right? So it's X arrow star, right? You remove all the X's. Okay. Does that make sense? So this is a cleaned up version of the scribble we have on the previous slide. Yes?
How are arrays handled in this?
So arrays are a whole bunch of, we'll talk, when we get to point analysis, we will talk about how we deal with memory and memory models. So there's a broader issue of how do you reason about, so you have to have static abstractions of runtime blobs of memory, because an array can be unbounded in size. You actually don't know how big the array is. Statically, what we'll do is we'll have a representation for it, which we will give it a name, and then we will treat that as one blob of memory. And so what we can do is actually treat assignments in that big blob as just assignments in that blob and read out of that blob. That's one way to handle arrays. But arrays do complicate things a little bit, especially with array indexing. It's a lot harder to keep track of these things. And part of the problem is, when you have a write like this, and later on you have a read like this, knowing if this came from here, really, you have to figure out if I is equal to j. And that by itself is a whole other analysis, right? Figuring out if two variables I and j are equal. Because I and j are computed, so I and j can actually be expressions, right? More complicated expressions. So all this gets more complicated, absolutely. But the idea still remains the same, which is that we will have information on the edges, right? So the idea is this is a really simple example to get us kind of feeling for how this works. You will still have information on the edges, and you will still have these ways of kind of computing information, setting up constraints between the input and the output information that you're trying to compute. Okay. So we're not quite done yet with setting up all of our constraints. We also need to set up the constraints for nodes that have branches and nodes that are called merge nodes. We'll get to merge nodes in a second. So what's the branch? So what happens here? So that's a branch node. What do we do here? So we have an incoming information coming in. What do we do on these things?
What?
Yeah, I mean, we just copy them. And we just say this is just in and out, and one is in. And what about here? What? Whoa, okay, hold on a second. What is this merge thing? Is this a statement? I've never written a merge. When I program, I don't like merge.
It's a unique, node that you can add after any work.
Right, so what's nice, what you could do is after every time you have basically two pieces of control flow that come to the same place, we add these nodes or merge nodes, and they actually, what they do is that they allow us to write kind of the constraints for what happens when two pieces of information come together. And so here, intuitively, what this represents is that the control flow could either come from here or it could come from here. And so in this case, we do out is equal to the union of the two things, right? So we take the union of the two incomes. Okay.
Do compilers ever do anything where maybe two paired variables like on top of it that held on both sides of the merge, but the union wouldn't hold? Do they do stuff like that? Or do they not give up?
Yeah, there's a lot of weird things you can do here. And we'll see how this actually, and sometimes it's not just union. It can actually be very cleverly. Yeah, I mean, we'll actually see how in some cases you don't want it to be just union. You can actually get information. I mean, you can actually do several clever things, more clever things than just union. In a lot of cases, it will be union. Actually, yeah, well, it won't even be union. It'll be something else, but it'll be a lattice theoretic operator. But we haven't talked about lattices yet. We'll get to that in a second. Okay. So now, okay, these things that we've just done, we've just written on these slides, they're actually called flow functions. And so all the constraints that we've written so far are basically of this form: out equals to f of in, and the f depends on the statement, right? So basically, these things are called flow functions. They're also called data flow functions, transfer functions in the literature. What they do is that basically give us some information before the statement f. What this function computes is the information after the statement. Okay? And so these are forward flow functions. They go in the forward direction. And you can also, in some cases, you can also have the flow function written in this way, where it's a function that takes two things, the statement and the incoming information, and produces the outgoing information. There's sometimes some things that you can have. So for example, you can have multiple input edges to a node, right? So here, this was like f of in. So when you have multiple input edges to a node, or multiple outgoing edges, and we saw this happens for merge nodes or branch nodes, it's actually pretty simple. So one thing to do is a flow function can take as input as two flow values, one for each incoming edge, and for the outgoing issue, the flow function can return either two flow values, or you can have one flow function for outgoing edge. Okay? That's another way of doing it. And there are other ways of doing this as well, and we'll talk about this a little bit later. Yeah. So this is okay. So flow functions. Yeah. Okay. Okay. Question on flow functions. Question on flow functions. So now, what we're going to do, and we're not going to fully do it today because we don't have time to do it. What we're going to do is that we're going to now say, so what do we want to compute? We want to compute some piece of information at every edge in the control flow process. So what I've done here is I've given variables to all So for every point, for every edge in the control flow graph, I've given it a name. It's a variable. I don't know what I'm trying to, I'm going to try to solve for those variables. I don't know what the result will be here. I don't know what the result will be here. I don't know, right? I'm just setting up all these variables so that every edge in the control flow graph has a variable associated with it. And then I can set up these constraints where here, this flow function is a flow function for statement 5. And what does this flow function do? It takes D10, which is the incoming thing here, and it sets up D11. So I have this equation that says that D11 should be equal to F from this statement thing, what's passed in with D10. And basically what I have here is I have all the constraints that I need to satisfy. Right? And now what I need to do is solve for all these variables, D0 through D16, subject to all these constraints that I have. I want to basically find a solution given all these constraints. We will do this, so we'll actually see how to solve this next time. What I want to do now in the remaining few minutes, so project is up. You should start looking at it right away because you have 3 weeks to do it. It's doable pretty quick. You have to start, you have to install LVM. You have to do a whole bunch of things. You have to get your setup working. For those of you who have groups, so you don't need to send me your group names. It'll become very clear once you actually hand in your first report, which will be due in 3 weeks from now, your 2-page report. You'll list all the names on your report. For the people who have a group, you guys are free to go. If you don't have a group, then we'll just hash it out here. We'll say, look, groups of 3, right? Not 4, not 2. Got to be groups.